Hello, I'm Roman. Welcome back to the series of the videos of building the convolutional neural networks from scratch. And the last video was, I think, already 1 week ago. And I had to take a break because I was actually very sick, and not only me, but the whole family. So it was like a couple of the tough days, but right now I'm more or less okay, so I will slowly get back to this series. But meanwhile, when I had some hours when I could think more or less clearly, I actually finished with correlate to D operation, at least the simplest version that I will need for the forward pass for the convolutional layer. Well, for the forward pass. For the backward pass, we'll need to integrate a different version. This one is called the correlate to D. Well, correlate to D valid, referring to the sci-fi package from the Python that has correlate to D function with 3 parameters and 3 different modes of the computation. So we'll have the valid one for the forward pass, and we'll need to implement the full one, which takes some data kind of outside of the input matrix to calculate the backward pass and actually to calculate the convolution, not the correlation, but the convolution. And yeah, so what we have, so we have the correlate to the operation. You can see that I changed the input parameters. So right now it operates on the matrix interface, and the matrix interface has 3 main methods. Transposing I'm not using. The main one is dimensions and the ability to get a value by the index. And we're starting from the comparing the dimensions because I assume that for the operation itself, we should have the same size between the matrices. Otherwise, we won't be able to do the sum of multiplication between the corresponding elements. And basically, the operation is like this. We go in through all of the corresponding elements, like ij, from both matrices, and we multiply the corresponding elements and we sum them, and that's it. And then return the value, and this value is going to be used as the new element for the result of the correlation. And correlate to the valid takes the input and the kernel. And before we go in further, we need to understand what is going to be the end size of the output. Currently, I assume that the input and the kernel respectively is the square matrix. At least in all of the tutorials that I've seen before, all of the ML models operate on the square images. So I don't think it makes sense to support the rectangle, but for now I will stick to the square. So we calculate at least for this operation, we take the size of the input, the dimension of the input, we subtract the size of the kernel, and we add in 1. And this is how we end up in the output. And then basically for the output, we go over all of the pixels, for all of the items of the correlate operation, and we take in we're taking a slice in a specific way. So we take in the I and j and we add in the size of the kernel. This is how we get submatrix from the input, and then we pass in the kernel, and we do the multiplication. Otherwise, if we get an error, which actually here we can have only 1 error, and this is not having the proper dimensions, return it. Other than that, we have the result. Okay, since this is the leftover, right? And we can take a look at the test. So yeah, I adopted the test. We check in for successful correlation, I actually can, how it was, now test, right? This one, yeah. Okay, so to run all tests, I'm leader key A. Okay, so we're checking for the error, and we're checking for the operation itself, checking for the full correlation. So right now you can see we have, for example, an input of 3 by 3 and kernel 2 by 2, and we have some results. So yeah. And another thing that I started to build is actually a convolutional layer. I added some placeholders for interface, for the function that I need to implement for the interface that is called layer interface. And this is the one that is actually used in the model training. Where this train. This is how we iterate over where it is forward. So this is actually used here. So we have the layers, which are the layers interface, and we have the forward method that takes the output from the previous layer and yeah, basically this one, and calls the forward for each of the implementation. For example, we could have a various of the implementation, for example, for the linear activation, like for the activations for the dense layer. I think the main one is dense, this one. This is how the forward looks like. But for the convolutions, I will actually need to think if it still makes sense, because between the convolutions, I guess I can represent the output, but I'm not. This is the thing that I'm going to face later once the convolution is implemented, because, for example, in the dense layer and in all of the activations, there is one input, one output for the forward pass, and two set of the adjustment for the loss, like the inputs and devices. For example, the inputs, right? How to properly the inputs where, yeah, well, actually the D inputs. But for the convolution, it's going to be this is going to be different. Again, I prepared, like, we have the input, we have the output and the inputs, and I added it just to confirm for the interface, but let's see how this will go. So I'm using this. So I'm using this one for now. Well, actually, I'm using various of the articles, and it's hard to talk when you're not fully recovered. Anyway, so this is the build with CNN from scratch. I will use, again, I'm building this on top of the neural networks from scratch that I implemented like on my previous series of building neural networks from scratch in the Golang, and I'm building on top of this. So what we did, I'm going to use the same data set. So first we need to instantiate the variables, and this is interesting because the convolution has the input shape, the filter size, and the number of the filters. I'm thinking how I should replicate this. So I have the number of the inputs, which for example, if we take a look at the dense layer, right? So we have the initialization methods, and the number of the inputs replicates how many samples we're going to pass into into the forward method, because if we take a look at the train, right, where it's actually used, no? Session, wait. No, it's data sets and flash mode. This one. Yeah, you can see there is a number of the inputs, which I can get from here, and the number of inputs here is, well, X is okay. Training data set, the load, and we returning the oh, it's actually okay. Now I'm recalling. So it's data length, so it's size of the pixels, right? Okay. Okay, so we have, for example, okay, it's the binary methods where they have the fashion. Okay, we have number of the inputs and the number of the neurons. Okay, so the number of the inputs is actually number of the pixels that we had before. The number of the neurons is the number that, well, we create internally for this one. So here, I guess it's going to be different. So the input shape. We actually don't need the number of the well. So what we need to have, so we have the output shape, number of the filters, input shape. Okay, what is the result? So the results, okay, so there is an input data. This is what we need to test. So there is an output. Okay, so the output based on the output shape. And the output shape is the correlation between the input data and actually output. I don't like Python. Okay, so it's a number of filters. So it's actually a 3D, three-dimensional array. Number of the filters, and so it contains all of the filters of the output size. So we have, for example, 3 filters, we'll have 3 matrices, and that will be the output. And what is the filter shape? No filters, filters. Okay, so this is the actual filter. And this is how, okay, so this is actually array of 2-dimensional array. And same for the biases. Okay, so it's actually biases and filters. This is what we're going to change. I mean, this is what we're going to adapt through the training process. So, well, backward. And output, this is what we're going to calculate during the forward path. And here we have to remember just the... Okay, so basically the filters should look... Filters is actually should look like this. So we have the filters, which is like this. I think that's the right thing. Then we will have this, right? And the output will be this. Yeah, this is interesting how I'm going to conform to it, but I know. So we don't need number of the inputs, we need the filter size, we need filter number, right? Input shape. What is the input shape? Input shape, I think this is the image, right? And where are we going to use it? I want to have an example. Train the network. Okay, the convolution train.shape. So okay, so this is the image size. Okay, let's make it more or less similar, so I can easily understand it. So that means is input shape, and this is int, right? Filter size and number of the filters. So there is no way I can use a tuple. Type. But okay, it's going to be square, so okay, input. Okay, this is going to be int. Like this. Number of the filters, I'm not sure, and the input shape, I'm not sure that we need to store it, but I mean, okay, let's do it for now. So we'll have the input shape, which is int. We have the filter size, I don't know, filter number, and again, that's int. And what we're going to do, we have the layer, the input shape, we have filter number, and same here, right? So now we need to actually allocate, and I think that should be the same here. And we have this, and just see, training 1. Okay. Then what do we have? So we have the filters. Make. We have an array of the dances by the filter number, right? Yeah, we have the filter and output shape. I don't want to. I think I can calculate it later. I don't need now. I need to create this. I need to create the filters and the biases, right? So we have the filters and the biases. So we have this one. We have the biases. Rand, where I use randomization. Let's shuffle. Rand D. Rand N. It should be this one. Standard normal distribution. We used before standard normal distribution. Okay, let's do this for right filter number, which means the layer, and actually need to allocate new. And what do we have for the filter? We have the filter size, right? Filter size, filter. And how I can create data rand float, how it was rand float 64. But then remember if layer filter rand, I think there is one for the 0, but 2 they have something for rand. Zero. Okay, so nothing for the 0, which means that I need to do the same for the biases. And I think it's not the right random. And this one. Okay. Okay. For filter size or layer returns a normally distributed float 64 in the range with a standard. Yeah. And same. Okay, so this is how we initialized this one. So currently we have filled deweights and debiases. I would not need, and actually not sure that I need the inputs. Again, too many questions. But this is the initialization, so we actually have the filters. I'm not sure. Well, the output, I mean, the output definitely should be by the number of the kernels. Because what is the output of the convolutional layer? It's the number of the computed kernels. So for example, if I had 3 kernels to calculate, then that's it. Interesting how I'm going to pass data and okay. I have too many questions now. Okay, assuming this is now the first is okay, for the forward pass, this is what we checked. Traditionally, convolution involves flipping the kernel by 100 degrees before performing the element-wise multiplication and accumulation. However, in the CNNs, libraries such as Keras and pytorch do not apply this rule of flipping the kernel. They perform a cross-correlation operation without kernel rotation. The decision to omit the rotation in this library is based on the practical considerations in the context of the CNN. The exact orientation of the kernel is not crucial for feature extraction, and flipping the kernel is unnecessary. Okay, so there is a forward. And for the forward, there is actually That's an interesting thing, because in the inputs, right? So we have rows. Each row is a sample, an image. For question, it's grayscale image. Because if we take a look, for example, at run question model, there is number of the inputs, meaning that it will take like this number of the input nodes in here. So there is an input data. And I guess we need to store it anyway. Inputs equals to inputs, right? We're storing it anyway because we'll need to use it for the backward processing. Now that we need to initialize the input. Initialize the input value. Well, actually we need to initialize the output value. Applying the relu activation function, I will add it as a separate thing, and it's actually interesting how I'm going to do this. It feels like I will have to merge all of the things, but I'm not sure. Okay, so the output is actually zeroing by the output shape, which means that we have the kernel and the size of the output. We have a function that computes the output. And it's actually right? So this is how we taking the S is actually the results, right? And we need to allocate, well, first actually layer in the output. Okay, this is going to be layer filter number. Yes, so we will have the number of the inputs. Actually thinking merge. Those are the questions I need to think, because, for example, going over the number of the filters, and I mean, so there is an input, which is actually, what is n? N is layer inputs. Okay, so the layer inputs. What is the kernel? M is actually layer kernel filter Okay, yeah, probably it's better to store it. For example, we could have the filters. This is the... No, it's a number of the filters. Wait. Okay, we have actual layer filters. We have the first one, we have teams. Okay, so basically, okay, for the number of the filters, okay, we have I or I layer filters number. What we do, we have the layer with its output, we already allocated this line, so we can index it, and we do this new dense. Then we have s and nil, because what we can do is actually this one. So we have the zeros, and then what we can do is output. Oh, but I don't need to zero it, and I don't need to allocate it. And then we have ops, right? We have correlate to the valid that takes input. Okay, so it's not actually that simple, because I can store samples. I mean, okay, what I'm struggling right now is that the items on the rows represent the image. Every row is the second, next image. So for example, for dense layer, if I want to train on one image, I would just, inputs will be the size of 1 by the size of the image. And here it adds another complexity, because I have actually fewer, I have several dimensions. First, it's number of kernels, then number of samples, and then I have the image data itself, which is to the array. So it's actually 4-dimensional array, well, at least 4-dimensional data. So the output could represent every index in the output could represent the kernel for kernel result for all of the samples that were passed. Okay. Okay, it seems like I need to think about this, because this is the part that I need to think better how to organize. And yeah, at least I got back to the recording of the series, so it's already a good progress for me. Yeah, if you have any ideas how to structure it in a better way, maybe restructure what we had before in the neural networks from scratch series, that would be better, because previously it was designed for the forward method to handle several samples at once, and all of the matrix multiplications were happening across many samples at the time, not just one sample. So for example, for the detecting the category for the clothes, it happened, for example, 100 images at one epoch, and forward corresponds to the one epoch of the data. So I need to think how to structure it better. Again, if you have any ideas, feel free to share. But for now, I see you tomorrow. Thank you for watching, and I see you in the next video. Bye-bye.